Today, let's take a look at how processes actually work. So we're going to see a demo of processes being created, the fork system call, the wait system call, and so on. This should give you like a more concrete understanding of how processes work. So we're going to work through some of the examples from Remzi Arpachi-Dessau's, Remzi and Andrea Arpachi-Dessau's 3 Easy Pieces, which is one of the books that this course is based on. So let's sort of like take a look at the first file here on my laptop. So all this example is doing is it's a very simple example. So one system call for you to know pretty quickly is get PID. So what this does is all it does is get the process ID of the current running process. So as you remember from some of our previous units, each process is uniquely identified by a processor ID, a process ID, and getPID just acquires that for you. And so every time you run this program, you're going to get a different PID because the process that runs is going to be different. So it's a dynamic property of the program. So first we print hello world, and then like we print the current ID of the process. And here what we're doing is we are calling the fork system call. So this is a very interesting system call. So what fork does is it creates a new process. So you must have been wondering, right? Like, how do you actually create a new process? So this is how basically. So fork allows you to create a new process, and the interesting thing about fork is that it replicates the process that is calling fork. So let's say we were process 1 and then we call fork. There's now a process 2, which is an exact replica of process 1 modulo a few details, right? For example, like what is the return code of a fork, right? So if the return value is anything below 0, it means that the fork failed, and this could happen because of a number of reasons, right? If you remember, a process needs a stack that it can work on, needs a set of registers, an instruction pointer, and so on, right? So perhaps it is the system is out of memory, and you can't actually allocate any new processes, right? And sometimes there's a limit on how many processes one process can create. So if you have created like a bajillion process, like there may be a system limit which says that's enough, like you're not going to be able to create any more processes, and so fork could fail. So in any case, a return value of 0 or less than 0, would indicate that fork failed, and it is good programming practice to catch this return value and to actually sort of like handle it, right? So here what's happening is that we're checking the return value, and then we're seeing that it's less than 0, and then we say that fork failed, and we exit the program with a code of 1. Now if you've been doing C program for a while, you would have seen that like the way C programs always end is like with the return 0, right? So what it means is the program is returning its own sort of like error code to the outside world, and 0 means everything went well. 1 means everything did not go well. So since we saw that fork failed, we are returning an error code of 1 to the outside world. So if the error code is 0, right? What it means is that the process, we are now in the child process, right? So this is where it gets a little bit weird, because at the time you call fork, and like at the return of when fork is done, like you are here, right, in both processes. So in the parent process, you return, there is an RC, and then return code, and then a child, there is a return code, right? So in the child, the return code is 0. Right, so that's how you differentiate between the parent and the child. So when fork finishes successfully, it creates another copy, and then in the copied process, what happens is that the return value is set to 0. Whereas in the parent process, the original process which calls fork, the return value is the ID of the process that was just created, right? So we use this to figure out whether we are in the parent or in the child. So we look at the return value, and if it's 0, we see that, oh, hey, I am the child, and then it prints the ID of the child process. And if not, we are in the parent, so we just need to print the return value, right? And then the return value is actually the error code, the ID of the child process. So let's actually see this in action, right? So we've compiled a bunch of stuff, And so here we see that we have hello world, and this is still the parent process, which is 74 is the parent process. And we see that the parent, the child process is 75, and then the parent prints out, hey, I am the parent of 75, my own ID is 74. So we've seen there is both a child process and a parent process, and we've seen that both of them sort of like execute, and we see their output. Right. So one thing that we should note here is that the order in which these two print, right, is not deterministic. So for example, after hello world, you have now the parent process and the child process, and either one of them could actually execute at a single point of time. Now in our sort of experiments so far, we see that parent always prints first, but this is not strictly required. So that should give you sort of an understanding of like how fork works, and like how the parent process and the child process execute, right? Let's take a look at a different system call, which is like just like a variant of this, right? So once again, we have the same program. We are calling fork again, but this time what we're doing is that we are waiting, right? So we're waiting in the parent, and what wait does is it waits until all the children finish executing, right? So if you look at the return code of wait, that will actually tell you like which process you are waiting on, and that just got finished, and so the parent process can run. So if you use wait, it is a way to deterministically force the parent to wait until the child has finished executing, and then the parent can continue executing. Now the reason for wait is that often you need to synchronize between your parent and the child. For example, the child could actually be created so that it can do a certain amount of work. The parent is waiting for the child to do this work. And so before the parent can go on and do something else, it needs the result of the work that the child did. So you do a wait in the parent. You now know that the child has finished, and then you sort of like use the results of the child, and then you continue executing. So wait is a very useful system call in this way, and so we're actually going to see like what happens with wait, right? So we already did a make, and so here once again, what is happening is that the child is being printed first, and then we have the parent, right? And so I'm not sure if you noticed, but like there's actually like a gap between like the child finishing execution and then the parent printing. This is because of the system call, the wait system call that we did. So with the wait system call, we are guaranteed to deterministically have the child print first, and then the parent, right? So this is a very this is just a small piece of code to demo that you have children and parents, and then you can wait for these for this relationship. So if you look at our next thing, right? So here what we are demoing is like, let's say you create a child and you wanted to do certain work for you, right? How would you do that? Because like what you've seen so far is that there's fork, and fork creates a copy of your parent, right? So that's actually not very useful, because like if the child is just going to do what the parent is doing, that's not really a very useful system call. So Unix and Linux actually do provide a way to have the child do something else, and that is what we're going to look at today, right? So we're looking at a system call called Exec, and there's a whole family of these Exec system calls, and we're looking at a particular variant called Exec VP. And what Exec does is you could create a process, and then when you call Exec will take a program that is currently lying on storage, and then it will load it into memory, and it will run that program, right? So let's say in this particular example, what is happening is that we want to run word count on the file that we are executing, which is p3.c. So you want to see how many words there are. And we're going to create a child process, and then we're going to have the child do the word count, and then it's going to finish, right? So we are using the child to basically run word count, right? And the way we do this is through exec VP. So if you go back and look at the code, so we have fork as usual. So at the end of this system call, we now have two processes which are executing. We condition on the return value, so we now know that we are inside the child, and we print that we are the child and so on. And since we want to execute word count, what we do is we pass these arguments to exec VP. So which is basically the arguments for the program that should execute. So in this particular case, what we are executing is word count WC with the argument p3.c. There are no further arguments, so it says null. And this is just as you would do it on the command line, right? So WC is the first part of your command, and then p3.c is the second part of your command. So you pass all of these things to exec VP, and the interesting thing is that like after this, nothing should print out. And the reason is exec VP, if it finishes successfully, will actually overwrite your child process with word count. So after this, like nothing we say or do will matter if exec VP finishes successfully. So in a sense, like what we're really doing is like we are brainwashing the process, right? After that, it has no concept of like what it was doing previously. All it knows is that it's a word count program. So this is basically how in Linux new processes are being created to do useful work. And let's sort of actually see this exec VP in action, right? So we do make, and then nothing has changed. So if we do p3, right? So here's what's going on, right? So initially this is the parent which prints out like hello world, and then the child prints out hello. And remember, because we're doing a wait in the parent, this will always print in this particular order. And after the child says prints out hello, we see this line which is basically the output of word count, right? So if you do like word count p0.3, this is exactly what you get, and that was printed out by our process, right? So we can actually modify it a little bit and see, like for example, if we do ls, like what happens. So let's actually change that, and let's actually do ls for the current directory, and let's try that. So now you can see that we have hello world, we have hello world child, and then the output is coming from running ls. And then once ls finishes, then we have the parent printing, right? So if you think about it, right, like what you have really done is you have written, if you wrote p3.c, is you have written a very, very simple shell program, right? So whenever we do any programming on the terminal, something like this, we are very used to having a shell, like, and most people use like bash or CSH, or the one I use is called fish, and so on, right? So the question is, you use the shell to run programs and to do compilation and so on and so forth, right? The question is, does the shell need to be part of the operating system, or is it just like another user program? And the answer is, it's just another user program, right? So the shell is not doing anything that requires user privileges. And in fact, if we took what we did p3.c and we sort of like modified it a little bit, we would actually get a shell. Because how does a shell work? It spawns new processes to do whatever command that you input, right? So right now in p3.c, we are saying like deterministically do ls or word count or whatever. So if you modified p3 a little bit to say get some input from the user and then run that command, what you would have is basically a shell, right? So writing a shell is actually not very hard, and so that's why there are like so many different variants of shell. And so now you have a little bit more understanding of like how bash or CSH work. Let's look at like one more program which illustrates like opening a file and redirecting output of a file and so on. So here we have another variant of like what we were doing before. So we once again have fork, so the child process is being created, and then now we are inside the file, right? Now what is really interesting here is that like what we're doing is we are closing standard output. So one thing if you guys should know is that there are 3 standard file descriptors that every process gets. So what do I mean by file descriptor? So every time a process opens a file, it is assigned a unique ID. So let's say you open like p4.c, that will be given an ID like 123, and then from there on inside the program, anytime you want to read and write to that file, all you do is just say I want to read 10 bytes from 123, or I want to write 10 bytes to 123. So you don't carry around the name throughout the program. You just like assign a number to it and then you use that number. The first three numbers 0, 1 and 2 are special. So 0 is standard in, 1 is standard output, and then 2 is standard error. These three file descriptors are set by default when a process is created. So every time you want to print something to the screen, what you're actually doing, if you go look at the GCC library, is that when you do printf, for example, that actually gets resolved into a write to standard output file descriptor, right? So that's really what is going on. And what is sort of like interesting is that if you so let's say you have let's actually like do it on the laptop, right? So let's say you have printf hello, right? And that I told you get resolved to a write system call, which basically goes to, let's say, 1 hello. So because like because 1 is standard out, right? Now the really interesting thing is, like, if you just execute this program, what will happen is that it writes to 1, and then which is standard output. But if you do something like close 1, just like writing pseudocode a little bit here, and then you open some file, this file will be assigned a descriptor of 1. So if you go back to this line where you're writing hello to 1, instead of like going to standard output or to your screen, that write will go to that file. And this is all without having to rewrite this program at all, because like the program thinks that it is writing to 1, and then 1 used to be standard output, but instead 1 is now actually a file, right? So that's really like the essence of what this particular program is doing. So we are closing the standard out, right? And because we are closing the standard out and we are opening a file, this file will be assigned the same number as standard out, because the way file descriptors and these numbers are assigned is it picks the smallest number that's available. So you closed standard output, so there is a gap, there's like 1 that's available. So next time you open a file, that gets assigned to 1. So now we once again, we are calling word count. We're giving it the parameter p4.c, then we're executing it. Now the key point to remember is that we didn't actually modify word count at all. Like we don't have the source of word count, so we don't do any changes to word count. But instead of like printing its output to screen, it will now put its output inside a file. And we're able to do this outside of the program without modifying the program in any way, because of the way the file descriptors work in Unix and Linux, right? So let's actually see this in action, right? So let's do make, and then let's do p4, right? And so now p4 didn't actually print anything, right? So if we go look at our list of files, we have p4.output, which is the file that we created, which has our output. So we were able to redirect the output of the process that we created to a file without modifying the program in any way. And this is really the concept of files, right? So for example, let's say I do ls and then I pass it to word count, right? So what this particular program is doing is how many words are there in ls is what word count is counting. Usually you pass, like, for example, file name to word count, and that's what it operates on. But here it's operating on top of ls, right? So this is the concept of pipes in Unix as a really powerful concept. The output of one program becomes the input of another program. And the way you're able to do all of this is very simple, just by closing file descriptors and opening another file descriptor. If you're writing your own shell, this is something that you'll have to know. And it sort of illustrates how powerful Unix is with very simple abstractions. So next we'll actually sort of like look at threads and why threads are needed and how they work in an operating system.